All right, quite a few people asked in class about number 24. This is a no calculator problem, which means things will end up pretty nicely. So recall that the area of polar functions are based on sectors of circles. In this area of the sector, if the central angle is measured in radians, is simply 1/2 times the angle measure times the square of the radius. So for any curve, this won't be the curve of a circle, but for any curve, we can, with a definite integral, accumulate a bunch of areas of sectors which approximate these regions. Since this isn't a circle, they're not sectors, but as the number of specific subintervals approaches infinity, the sum of all those sectors will become exactly equal to the area between the polar curve and the pole as you rotate. So we just use this 1/2 times theta times r squared. And what's going to 0? If we increase the number of regions to an infinite number of regions, it'll be the difference between every rotation, the d theta. Therefore, the formula that we should have memorized for polar areas is from theta equals a to b of 1/2 the radius squared d theta. That's it. So for this problem, we need to solve for r. That's pretty easy. We just divide both sides by cosine of 1/2 of theta, or cosine of theta over 2. So the right side is 1 over cosine of 1/2 of theta. All right, so our answer then to the area problem is 1/2 from 0 to pi over 2 of that squared. So 1 over cosine of theta over 2. This is our r value, so we're going to square that d theta. And if you do 1 divided by cosine, then that's secant. So this is 1/2 of the definite integral from 0 to pi over 2 of secant squared of that same angle. And we know that the antiderivative of secant squared is just tangent. We're going from 0 to pi over 2. So this equals, let's see, tangent of pi over 2 would be tangent of pi over 4. Tangent of pi over 4 is 1. And tangent of 0 over 2 is tangent of 0, which is 0. So we have 1/2 of 1, which is 1/2. Choice A.